Hello, hello. Welcome to this lecture. We're continuing with modular arithmetics, divisibility and primes. Let me switch my laser pointer thingy. Okay, so first concept, even when we say evenly divides, we mean that x evenly divides y if y is a multiple of x. And we denote it with this symbol, which stands for x evenly divides y. Okay. Another way to say this is that y is a multiple of x. But another one is to say that x is a factor of y. And by the way, you can keep counting. I mean, like post on Twitter or something or on a chat. How many different meanings we have of this sign by now? Okay, so somebody who like gets the most will win. Okay, concatenation, excellent. But there was more. Okay, let's go. Yeah, post it. So a number is a prime if it's a positive, and its only factors are trivial. So it's itself or one, right? So a number p always divides p, right? And a 1 divides p, but these are trivial factors, like you don't have to think. Okay, like I give you a number like 37, and you know that, okay, it has factors, 37 and 1. But these are trivial ones. Is it a prime? Is the question, are there any non-trivial factors? Okay. So if a number that is greater than 1 is not prime, then we call it composite. In other words, it has some factorization that is non-trivial. So it breaks into two factors. Perhaps they factorize even further, right? But the two factors a, b, such that a times b equals that number n, and both a and b are smaller than n, right? With trivial factors, a and b, one of them would be 1, the other would be equal to n. So you didn't decrease, right? By factorizing, you are stuck with the same number that you have already. The composite one is the one that can be broken in represented as the product of two smaller things. Smaller, but non-negative. Okay, so the fundamental theorem of arithmetic is that every integer can be uniquely expressed as a product of primes. And it's unique by up to ordering, right? So there's a natural way ordered from smaller to larger, right? So for example, 120 is 2 to the 3, which is 8 times 3 times 5, right? It's 8 times 15, 120. So, and this is unique. There is no, there are no two ways to factorize 120, except of course you can reorder these, but that's not interesting. Okay, so that's always the case. And without lots of generality, we can represent here a string of all primes, p1, p2, p3, p4, right, which are consecutive primes. And there is always every number corresponds to a unique exponent string. Some of the exponents could be 0. Like, for example, you can think of this multiplied by 7 to the 0th power. And then the next prime would be 11 to the 0th power. So in fact, all the next primes are zeroed out. But it's still a unique sequence, right? You can represent every integer as such sequence of powers in this representation. Two other concepts: least common multiplier and greatest common divisor. So least common multiple, of x and y, abbreviated LCM, is the smallest integer that is multiple of both x and y. Okay. So there is always a multiple of both x and y. Just multiply x and y, right? That's going to be a multiple of x and multiple of y. But perhaps some smaller one is also. Like, for example, if x divides y, then least common multiplier is just y, because y is a multiple of y, and also y is a multiple of x in this example. Greatest common divisor is going the other way. X and y can be factorized fully, and then some of these factors might be in common. The greatest common divisor is all the factors that are in common to the maximum powers. There's a related concept. We call x and y relatively prime if they don't have common divisors. If the only GCD of two numbers is 1, that means that the factorization of x and the factorization of y had no primes in common at all. And here is a general law. The least common multiple multiplied by the greatest common divisor is the product of the two numbers. So watch some examples. So here I have some integer which is cooked up as a product of these following primes, right? With the multiplicity of 5 is 4. So it's 5 to the 5 to the 5 times 5 times 5 times 5 times 5, right? 3 times 3 here. And this has a factorization like this. So what's the greatest common divisor of these two? Well, 7 divides this guy, but not this guy. So 7 is out, 11 is out, 13 is out because it divides only this one, but not that one. What's in common between them is multiple some factors of 3 and some factors of 5. But how many? Well, a single one of 5, because this guy is divisible by 5, but not by 25. This guy is divisible by 25, 125 by 225, yes, but this one is not. And also both of these guys are divisible by 9, 3 to the 2, but not by 3 to the 3. Okay, so the GCD is the highest possible power of 3 that is present in both, times the highest possible power of 5 that is present in both, and actually highest possible power of all the other primes that is present in both, because there is a hidden 7 power here. It's 7 to the 0, and a hidden 11 power, it's 11 to the 0, etc. The least common multiple is going the other way. It's the maximum of these. So it's 3 to the 5, and 5 to the 4, and 13 to the 2, right? And 7 and 11. This is the smallest number that is going to be a multiple of both of them. And this is the greatest number such that both of these guys are multiples of that one. And they indeed have to multiple to the given numbers. Why? Because in GCD, you take the representation and the exponent, say I and j, and what you take is the minimum of these two exponents. And in LCM, you take the maximum. And because minimum of two exponents and maximum of the two exponents is the same as the two exponents added, that's true. So this in the product, this is a sequence of all primes with the exponents that are the minimum ones. This is the sequence of all primes with exponents which are max. So when you multiply, you add the exponents. And here too, this is a sequence of product of primes with exponent I. This is a sequence of primes with exponents j, for every prime that's focused on each prime in this sequence. So in here, the exponents would add, and in here, the exponents would add. Hence, this implies that. Okay, you can write it out, okay, but let's leave this for now, right? You can check in the book if you are not sure what I was talking about, or derive it for yourself, even better. Okay, factoring. So, okay, so I'm talking about all these factors, right? Like there's integers, and like, for example, here, hey, somehow I knew that the factorization of this is this stuff. Of course, it's the other way around. I first wrote this, and then I computed that, right? Not the other way around, because, yeah. But in general, how do you go from a number like this to its factorization? Okay, well, here is a trivial algorithm. You could just iterate through all the integers and check whether this integer divides n. Okay, you would always get a factor in that way, or you would return prime if there is none. Okay, and you avoid the trivial ones, which is 1, and the final one, which is n. Okay, so this is great, right? The algorithm exists, except that it's horrible as a running time, right? So if I ask you, like, for cryptography, I give you a number that has, you know, hundreds of digits. If you wanna run from check all integers between 2 and that number, you know, you would end forever. You would run for you know, as long as the age of the universe or more. Okay, here is a slight improvement. Go to just the square root of n, right? Because if you haven't found anything past square root of n, then you're not gonna find anything, right? Because if x reached square root of n, then this thing now becomes smaller than square root of n. So you must have encountered it already. But that's not much of an improvement, because if my n for cryptography has, you know, hundreds of digits, then square root of n will have 50 digits, and that's still not good enough. Yeah, you cannot. That's too big of a number. Okay, so if I try to go over 100-digit numbers, okay, so this would mean how many numbers are between, you know, 1 or 2, right, and some 100-digit number, 2 to the 100. Right, because for every, sorry, 10 to the 100, because for this is decimal digit. For every digit, you have 10 choices. And 10 to the 100 is a lot. You know, even if the inner loop took like 1 nanosecond, then it is still not enough. You know, nanoseconds in a year, it's basically something on the order of 10 to the 18. So you would reduce 10 to the 100 by just a factor of 10 to the 18 in terms of years of computation that you need. Yeah. So this is because this algorithm is exponential in the number of digits. So basically, it cannot it's not feasible for large numbers. What we would like is to have an algorithm that is polynomial in the number of digits, right? So rather than exponential. So factoring is in classical computing, there is no algorithm. We don't know of any algorithm that would factor numbers, all numbers. Some, you know, some subclasses of integers can be factorized, but in the worst case, I create the numbers in a certain way, and that's the basis of RSA crypto system. Actually, there is no algorithm that factorizes them fast. In particular, by fast, we mean polynomial time. So there's some degree, like for example, third, and I want to run number of digits to the third power. Okay, perhaps, okay, fourth power. Of course, you know, if you give me an algorithm that runs to the 10th power, maybe for, you know, it's still not good enough really for large n, but that would be a huge breakthrough. We don't know of anything of that form. Now, in quantum computing, however, this was one of the first algorithms shown that if you had a quantum algorithm, if there was a quantum computer, it is actually somewhat easy, you know, once you get your heads around what the quantum computation it could do, you know, what are the basic operations of quantum computing, then it was one of the first results that showed by Shor, you can factorize in a quantum computer, right? So this is, well, it's part of why it's so important whether quantum computing can be made feasible, right? And there's huge research and engineering effort on developing basically quantum computing prototypes, which are, some incredible amount of money and resources go into trying to construct them. Okay, so here is the factoring problem, but here is a different one. Instead of, if I give you an integer here, and I say, give me either an answer that it's a prime, but if it's not a prime, then don't just tell me it's not a prime, actually give me the factors. Here is a different problem. Just tell me whether it's prime or composite, okay? And if it's composite, then if you just tell me it's composite, that's fine. You don't have to give me the factors. In computer science, this is known as a decision problem, and this is known as a search problem. So, everything is divided like this. Like I give you a Boolean formula, and I just ask you, is it satisfiable? Is there any way of assignment to the variables that makes the formula true? Yes or no? Versus, okay, if it's a yes, then find the assignment, show it to me that there is an assignment of the atomic atoms in the Boolean expression that makes the solution true, that satisfies it. And many other versions of this. It's all over. You can pose problems in a decisional way or in a search way. And sometimes the two versions of the problem are equivalent. And here it is not known that they are. In particular, there is an efficient algorithm that just tests primarity. So solves the decision problem. But it's somehow that algorithm, in fact, there's many such algorithms, none of them solves the problem by finding factors. They have some other, how do you say, evidence that the number is composite, but this evidence is not in the straightforward way of finding factors and showing that, hey, here are the two integers, you can multiply, that's an efficient procedure. Definitely polynomial in the number of digits. How long does it take you to multiply? Square of digits, right? Because it's the high school, or elementary school algorithm. You write the two numbers and you cross multiply, right? And so that's a square, the number of operations in the length. Actually, you can beat that. That's a very non-trivial thing, and a kind of beautiful thing, and not that hard. So check on Wikipedia optimal multiplication algorithms. You can beat the square root bound. So this number, by the way, this algorithm for years, they were probabilistic ones. And then a researcher, and I should have the name here, came around from India, a mathematician, showed that there is a deterministic algorithm to decide this. In practice, which was a big breakthrough, it was unexpected. And people still though run the probabilistic ones because they are faster in practice. You will see in a second how they run, and you'll see why that's sort of plausibly suffices. Why are we talking about all these primes? They are used all over the place in applications of modular arithmetic, in particular cryptography, which will be sort of our pinnacle of this whole segment. Will show some crypto systems. So where why they need primes will be very apparent. But there is many other applications as well. Okay, so how do these crypto systems find primes? Because they need them. Well, so for example, a crypto system has something we call security parameter, 100, 150, 128, 256, let's say 200. It's like the crypto systems have known crypto analysis, which suggests how big the parameters should be to hit certain hardness target. And a hardness target is effectively this: I want to be secure against any algorithm that runs in the time 2 to the power security parameter. So 128-bit security means I want to be secure up to anyone who can perform 2 to the 128 roughly operations. And 80-bit security just means I want to be secure against anyone who can perform 2 to the 80 operations. Okay, so as time goes by, we need stronger security. That's why you might see versions of crypto systems for 128-bit or 160-bit or 256-bit, because we want to have a ramp up and ability to upgrade as computing gets faster and faster. Okay, so let's say you say, okay, I need a 200-digit prime. How do you create one? Pick a random number, apply the primarity test, and the primarity test will answer yes or no. If it says yes, you're done. If it says this number is composite, you just loop back. Pick a new random number, apply the test. In loop, however long does it take to finally hit this case? Now, how long will it take? It depends on the density of primes, right? Like how common are prime numbers. Let's say if in all 200-digit numbers, if I choose a random one, how likely am I to choose the prime, right? Whatever density of prime is, let's say that the probability is that 1 in every 10. So how many times will I run this loop on average? 10 times, because that's actually the meaning of probability. Probability is, the coin, random coin, is a probability 50-50, right? Or 1/2. 1/2 probability gives tail, and 1/2 gives a head. Why is it called 1/2 and not on some other scale? Because the meaning is of 1/2 probability is that in expectation, what you should expect is that 1 out of any 2 throws give you this result. So yes, so if 1 in every 1,000 is the probability of finding a prime among 200-digit primes, then it's 1 out of every 1,000 executions of this loop, then I will get lucky. So therefore, I will run it in expectation 1,000 times. This is all okay. You don't have formal probability, most likely, and we are not teaching it in this class. Like, if we're lucky and we get through all the stuff that we want to talk about, then in the last lecture of the quarter, we will upgrade counting methods to little lick of probability. But here I'm talking about probability, and I'm talking about expectation, concepts which are not formally introduced, okay? But I will just need them for this type of exercise, and I hope you're okay with this. Okay. So this gives rise to a question. Okay, so what is the density of primes? So Euclid showed that had a nice proof. It's not hard. That the number of primes is infinite. That there is no stop. There is no border beyond which primes don't occur. Okay, it's a very beautiful proof. Again, Google it. Because it's very concise and not obvious. Okay, so okay, but we don't need just the fact that they exist. We want to know like how common are they. So here's the prime number theorem. It says that if you look at the range from 1 to x for whatever x, then as x goes large, you can approximate the number of primes in this range by an expression x divided by the natural logarithm of x. ln stands for natural algorithm, which means it's a logarithm with base e. So, okay, and you can scale if you have a larger, if base E is not super convenient for a human, right? But you can convert base 2 or base 10 logarithm to base E with a simple relation. And I will have it here, but also if you're rusty on logarithms, now is a good time to read that section in the function chapter where I said, we didn't require it last time, but it was still on the syllabus. And I said, we will use it sooner or later, so read it, but now is the time if you haven't. Okay, so this means that the probability of encountering a prime in that range is roughly this. Okay, so therefore, how many times will you run this loop in expectation? The inverse of that, which is this logarithm. Okay, so in other words, if I say, for example, what's the, okay, but here's a little caveat. When I say give me a 200-digit prime, I want a 200-digit prime. That's a slightly different question because I'm not going, here is 10 to the 200. It's the end of my range. But it doesn't start at 1. It starts from the largest 199-digit number, which is 10 to 199. But notice this range is a 90% of this one, right? Because this one there's 10 to the 200 numbers in it. And what's missing here is 10 to 199, which is 1/10. Okay, so, okay. So by the same theorem, so what's the density of all those that you miss? It's a logarithm of 10 to 199. It's incredibly close. So the density in all of them and the density in here is really basically the same. Okay, there's a tiny difference between these. So you can approximate, even though the theorem says, okay, this is the density in this whole range, not in this subset. But first of all, it's in 90% of the set. Second, you can compute for yourself that if you kick out that part, you're not changing this substantially at all. Okay, so this will still be a good approximation to the answer like this. So what's the density in this range? It's natural logarithm of 10 to the 200. And for this, you need be able to translate between, right? Because if it was a logarithm base 10, then the answer is immediately 200. But it's a logarithm base E. So you just need to know the logarithm base E of 10 in order to be able to translate between them. And that logarithm is, hold on, let me move this thing, is 2.3. That's the logarithm of 10 base E. So therefore, logarithm base E is 2.3 times about logarithm base 10. And the logarithm base 10 is just the number of digits, right? So how many times you need a loop to generate a 200-digit prime? 200 times 2.3. So it's 460, okay? And that's a good approximation. Which is not great because like 460 times I need to run and test the primarity, which is also not like blazing fast algorithm, okay? That's why we cannot have crypto systems where we pick a prime, too often. But in a system like RSA, you do it only when you generate your public-private keeper, and then you keep that public keeper for a while. So it's okay to pay that cost because it's only at the initialization. So how do you approximate? Okay, if I ask you, okay, how fast would find a prime in this range? So the number of digits here is 15. So so the probability with which you hit a prime here is one of a natural logarithm of this number, which is 2.3 times number of digits, which is 2.3 times 15. So, okay, it's 1 in 34. Okay. Okay. So, okay, so this is how, and I'm not going to tell you much about these primarity algorithms, okay? So if you take an undergraduate crypto class, then you will see them. Of course, you can read up about them. They have a beautiful structure, and they are probabilistic in that they also are internally picking some random number and doing some tests involving n and that random number. And if a number is prime, then they always say, yeah, it's a prime, it's a prime, it's a prime. If it's composite, with 1/2 probability they err, and they say prime, but with 1/2 probability they will say composite. That's not good enough. But if you repeat it 100 times, then and you answer composite if any of these 100 executions said composite. So the only way to say prime on a number which is actually composite is if each of the 100 instances erred. And what's the probability of that? 1/2 to the power of 100, because it's 1/2 probability that the first instance erred times 1/2 probability that the second instance erred, right? Because it has to err each time. So, you know, if I do it 3 times, the probability is 1/8. If I do it 4 times, the probability is 1/16, and so forth. And by the time I do it 80 times, and the probability that I err is 2 to the minus 80, that's okay. Okay. So there is lots of inner loop, right? But that's the nature of these algorithms. That's the best we know how to do, you know, so far. Computing. Okay. Now, finding whether a number is prime. Okay, I gave you these probabilistic algorithms, or SCAT, really. Finding whether a number is composite, okay, is the same probabilistic algorithm, right? But finding factors, actually, we don't know. But here is something that we could do. We could very easily compute whether two numbers are, what's their greatest common divisors. If we could factor both numbers, then of course we can compute the greatest common divisor, right? Like that was a slide few slides back. But without lots of, but in general, we don't know how to efficiently factorize. But surprisingly, if all we care is the common divisors of two numbers, then that we can actually compute blazing fast. Okay, and that would suffice for a lot of cryptographic applications. I will get to that in a sec. Okay, not a sec. Few minutes. Okay, so this is again, this is an algorithm that already has 2,000 plus years. Okay, so here's the algorithm. Okay, so just if you recall of the notations that we introduced, you know, at the beginning of this segment, the integer division of A and B is a quotient and a remainder, such that A is quotient times the divisor plus the remainder, where the remainder is in this range, right? So if these are the terms, and now, okay. So suppose I want to compute GCD of two numbers A and B. Here is a helpful fact. If let's order them, let A be larger than B, and now I want to find all divisors that are common between A and B. If I find all such divisors, then I can form a GCD, right? Because that's just the product of all those divisors, right? So finding GCD is like finding all factors that A and B are having common, find all common divisors of A and B. So let's say take some divisor. If this D is a divisor of both A and B, it's a common divisor between them, then D is also a divisor of A mod B. What is A mod B? It's a modular reduction of A modulo B. It is a number that is smaller than B and definitely smaller than A if I arrange them this way. So this is the larger of the two modulo the smaller of the two. This is basically the beginning of a recursion, because I had some two higher numbers and a question of finding divisors between them. And it turns out that if there is a divisor between them, then that same divisor is also a divisor of a number that is smaller than both A and B. Okay, so perhaps I can use it to start up a recursive algorithm. And it's an easy sort of fact to observe, because the remainder of the division, A mod B, of the division of A by B, integer division of A by B, A mod B is a remainder of that division. That means that there is some quotient that you can represent the remainder, meaning A mod B, as A minus that quotient multiple of B. So that means that, so here is the same thing, okay. So now if D divides A and D divides B, then A is some multiple of D and B is some multiple of D. And because R has this form, it's A minus quotient times B. So it follows that A minus quotient of B is also a multiple of D, because both A is some multiple of D and B is a multiple of D. So this is a multiple of D, this is a multiple of D. If I subtract them, I get still some multiple of D. Right, namely this one. But the point is that this is still a multiple of D because it's a linear relation between A and B. So I cannot lose a common divisor if I do a linear operation, right? If I do a, right, both of my term A and B are product of D, and I subtract one from another, so I get the product of D. Now, here is the opposite fact of the way. So if I start with number A and B and modulo reduce, so rather than consider A and B, I consider A mod B. It turns out I don't lose any common divisor. If there was some divisor of A and B, that is still a divisor of A mod B. This is what I just argued. For the recursion to work, it's not enough that I don't lose anything. So if the reduced problem has the same set of answers, is I also cannot create any, right? Perhaps A mod B has some other divisors which A and B didn't have, but that's not true either. If something divides A and B and also divides the smaller of the two, then it must divide the larger. Okay, so that's almost the same calculation, right? So if, because this is the equation, if R is a multiple of D and B is, then the whole thing is, and so therefore A is. So therefore, the following is the case. Two numbers A and B have any multiple in common, divisor in common, even only if the same divisor is also common for B and a strictly smaller number, A mod B. So my initial pair is A and B. And if I want to compute its set of all divisors of A and B, it turns out that this problem has the exact same answer as a problem of finding all divisors of B and A mod B. Now, what did I gain? I gain because these guys are, in some sense, strictly smaller. What is the sense? Any. Give me, for example, the max of these is smaller than the max of these. The min of these is smaller than the min of these. So clearly I'm progressing. If I now run a recursion and okay, so what's the answer here? I still don't know, but I do the same thing, which is, this is my new A, this is my new B, and I do the same trick. I replace them by this and a modular reduction of the higher by the lower. And that's my next recursion call, right? And I just recurse in this way. What I hit at the end? So what I recurse this way? What is the base case? Well, you can sort of see how it would act, and you can set up the base case in a different way. But here's a good way. One of them, the small one, at some point after the small one will have to divide the larger one. It might be trivial because the B is 1, so it divides everything. Or it might be non-trivial. B is, for example, 2, and A is some even number, or B is 3, and A is some number multiple of 3. At that point, you're done. In fact, if you try to do the next one, if A is a multiple of B, then what's A mod B? It's 0. And at that point, you're not hitting, right? Like the next time, anyway, modulo 0 is there's no such thing. So when you hit this case, B is your greatest common divisor. If B divides A, then the GCD of these two numbers is B. And by the recursion, it's the greatest common divisor of any previous pair you had, including, of course, the initial pair that you started. That's the Euclid algorithm. So the code is very simple, as is all beautiful recursive algorithm code. GCD of A and B is, if A is a multiple of B, then it's a B. Otherwise, run recursive. So the answer is the answer in a recursive call when I replace A and B with B and A mod B. Okay? And I loop and I loop and I loop until I hit this case. Right? So an incredibly concise recursive algorithm that does a very powerful thing. Find common factors without factorization, for which we know no efficient algorithm. There is a beautiful question that I'm skipping. Okay, so this algorithm is correct. How fast does it run? So, there is a factorization algorithm, right? Just iterate. It's horrible in terms of running time, but it exists. Is Euclid algorithm better? Yes, it is. Because there is a simple measure. I mean, one of them could be A plus B. Okay, it's like the total sum of this, of the inputs A and B, right? Okay, you know what? Let's take the following measure. Let's take a measure max of AB. Okay. I can show not hard that if I make 2 of these recursive calls, then the max of AB got halved. Not with the 1. Yes, because if I start with, like, say, you know what? No, yeah, I think the max is going to half just by single by single in a single call, right? Because A mod B, wherever B is, it has to be the A mod B has to be right. So A mod B is at most half A, but in the sequence of these numbers, right? A, B, and then the A mod B, which is at most half A. So if you do two jumps, you went by a factor of 2 at least. So that's exponential decay, right? If the initial number is say 2 to the 100, how many times do you loop? At worst, 200 times. What is that? It's twice logarithm base 2 of the initial value. And in terms of the number of digits, so I just gave you an approximation, right? An argument that it's the running time is logarithmic in the value. But if you think of not the value, but the number of digits, then what's the relation? It's logarithmic one. The number of digits is the logarithm of value. Therefore, the running time of this algorithm is linear in the number of digits. And the fact that it's logarithm base 2 in my argument, and actually there is another factor of 2 because I get a /2 with 2 hops of the algorithm, and not log 10 base 10. Oh, that's immaterial in a way because the logarithm base 2 and logarithm base 10 are related. How? By a multiplicative factor of log 2 of 10, right? Which is 3 point something. So it's just a factor in front. So the number of hops is 3 point something times 2 times the number of digits. Okay, so it's linear in the number of digits. Extended Euclidean algorithm. You can use the same algorithm not just to find the GCD, but to find something extra. To find two coefficients, S and T, such that you can represent the GCD as the linear combination of the two numbers. Okay, so and I'll tell you in a second why you need this, okay? But let's first see that it's happening, that it's true. You know what, let me just unwrap this algorithm. So look, it is convenient to think of these recursive calls of Euclidean algorithm. Here is the Euclidean algorithm in its entirety, even more concise. Okay. So let's call the initial parameters you call it on A0, B0. Let's say you call it on 259 and 77. The next call, recursive call, is on 77 and 28 because the new A is the old B, and the new B is A mod B, and A mod B happens to be 28. Okay, then what's happening in here? Is 28 divisor of 77? No. So you make a recursive call with new A being old B. So this is just get copied. And what's the new B? It's 77 mod 28. And that happens to be 21 because of this equation. All right. So this is the call. And now you see that the multiple is for sure 7, right? But how is the algorithm going to execute? Well, 28 is not a multiple of 21. So it's still one more recursive call. What's in the call? The new A is the old B, so that gets copied. And the new B is 28 mod 21, which is 7. Right? And now we hit the base case because 7 divides 21. So the 7 is the answer that the GCD algorithm returns. And indeed, you can check 259 and 77. There's only 7 in common. You can convince yourself easily. 77 is the product of 7 and 11. And the only thing you need to check is 7 does divide here and 11 does not. Okay, but you don't have to check, if you did all these steps correctly. Now, we can use these equations to find these two parameters S and T. Okay, so observe how this is done. I'll just do it on an example. This is a trace of my of this Euclidean algorithm. Okay, this is the important part. The first A and B is expressed in a linear relation like this, and this is my new B. And in every step, I relate the old A and B, A, B, to the new B, which is A mod B. Okay, so focus on these linear relations, that at the end of which you have the GCD, and at the beginning of which you have these two numbers. Now, I want to represent the GCD, which is 7, as a linear function of 259 and 77. Well, notice this guy is a linear function of 259 and 77. And I don't have in my hand this guy as such a linear function, but I have a recursive. This guy is a linear function of, the previous two. And this guy is a linear function of the previous two, where my, the sequence started with 259 and 77, and then 28, 28, 21, and 7. I know that this is pairs, but this guy in the pair is always a copy of that one. So I can write them on a line. 259, 77, and then 77, 28, and then 28, 21, and then finally 21, 7. And what I have is that the last guy is a linear function of the previous two. I want it to be shown as a linear function of the first two. Okay, so these are the linear relations, as I was saying, okay, that are basically come out of as you do the steps of the Euclidean algorithm. And now I want 7 to be a linear function of these two, okay? But what I start with is that I have a 7 as a linear function of these two, okay? So in particular, I mean, these are the particular, coefficients, right? 1 and -1. But now I can combine this, the fact that I know 21 as a linear combination of these two, and I know 7 as a linear combination of these two, I can combine these two. So to represent 7 as a linear combination of these two. And now recurse, and eventually I'll compute 7 as a linear combination of these two. So let's see. I want 7 as a linear combination of these two. And note, okay, I can do this using these two equations. I have 7 as a linear combination of these two, but also I have this guy as a linear combination of these two. So I just plug in this in here. And I notice that that 28 minus 21 is the same, right, as 28 minus 77 minus 2 times 28. So it's the -2 and plus, yeah, because it was minus this big bracket, so it became 3 times 28. And because I'm doing a minus this thing, so it's -1 times 77. All I did was replace 21 here by this. Okay, so maybe it's more convenient if I put the 7 on this side of the equation, but anyway. Okay. So now you have 7 as a multiple, as a linear combination, not just of these two, but of these two, 28 and 77. And you recurse, because now you replace 28 in this equation by this expression. And if you plug it in, it will be 3 times 259 in bracket, 259 minus 3 times 77. So you just cross multiply correctly, and the result will give you 7 as a sum combination of 259 and 77. Okay, so this is what I conclude from that. And now I use this again, right? I have I hate my own notes here. I will rewrite them because I don't know, that was my logic, but I don't think this is the best way. I would definitely put the 7 on the left hand side rather than the right hand side. But in any event, that's what's happening. I know that 7 is this form. Now I replace 28 here by 259 minus 377, and so it's here, and there is a 3 in front of the 28, so there's a 3 in front of this thing. Yes, sorry, I hate these notes. I will rewrite them. But hopefully you can still see what this did, right? I just put this expression into, I replaced 28 by this, okay? And because now I have 77 times some multiple and 259 by some multiple and 77 by some multiple. So I group 259 and 77 and I get their multiples. They happen to be these. Okay. Sorry. Okay. Repeating myself. I will rewrite this for this to be clearer. So you can the end message is that you can take these equations and work your way up so that to represent the GCD as a linear combination of pairs of these numbers, where the pair is at the beginning, just this one, and then we do the one more step, and it's now it's this one, and then you use one more equation, and it's this one, and so forth you go until you hit the initial ones, and then you get the coefficient you were asking for. Okay, right. All right. Why am I looking for this coefficient? Because this allows me to compute multiplicative inverses in a modular arithmetic. So if n is if multiplicative inverse of b if number a in this residue group, I denoted Zn last time, has a multiplicative inverse, that if this multiplicative inverse exists, we denote it b, and it has to satisfy this equation. So it's something that multiplied by a mod n gives you a unity. And then we can denote it as a customary notation for inverse, but it is not a rational fraction, okay? So everyone who, in this modular arithmetic segment denotes multiplicative inverses as a rational fraction, we'll just get 0 points on everything, okay? Which they use this type of notation because this is not rational division, even though we use a notation that is similar to that, right? But these things do not denote the same as a rational division. Consider multiplication table in Z5, right? We went over it last time. Every element here there is some value here that multiplied gives you a unity, right? So for example, inverse of 3 is 2, and indeed 2 times 3 is 1 mod 5, right? Because it's 6, and 6 is the 1 mod 5. And inverse of 4 is a 4 because 16 mod 5 is a 1. Okay, so these multiplicative inverses exist. Okay, let's look at mod 6. And as we did that, right? So I'm going fast. It's the same exercise as last time. For many rows, there is no unity. Okay, so for some rows it exists, namely 1 and 5. There's a unity here and there's a unity here, but everything else does not have an inverse. In other words, inverse of 2 mod 6 does not exist because 2 times whatever mod 6 is never 1. It's 0 or 2 or 4. Okay, and likewise 3 minus 2, inverse of 3 does not exist, and the inverse of 4 does not exist. Why is that? Well, the criterion for whether inverses exist can be expressed very simply in terms of GCD of a number and the modulus. The modulus here is 6. And note that the only numbers here whose GCD with 6 was 1, in other words, they didn't have any common factors with the modulus, were precisely 1 and 5. The two numbers which have inverses, and all the values mod 6 whose GCD with 6 was not 1, in other words, they had common factors with the modulus, the inverses for those do not exist. That's not a coincidence, that's a law. That's a general fact. So A has a multiple of the inverse mod n, even only if the GCD between A and n is 1, if they don't have common factors. That's why when you want to do modular arithmetic, all you need is fast GCD. Okay, and in fact it follows from Euclid's algorithm that A has multiplicative inverse okay, so A has multiplicative inverse only if it's coprime with the modulus. If modulus is prime, then nothing is coprime with the modulus. Sorry, if modulus is prime, then everything is coprime. In other words, GCD of everyone between 1 and n minus 1 will be 1 with modulus n. That's why GCD of all these numbers and 5 is 1, right? 5 has no smaller factors. So all of these numbers are coprime with 5, and all of them have inverses. These only 2, 3, and 4 have inverses because 6 is, only 1 and 5 have inverses. 2, 3, and 4 do not because 6 is not a prime. Okay. So there exist integers in Z6 that are not prime, not coprime with the modulus. Such integers not in Z5 do not exist except of 0, okay, which is it's obvious that 0 cannot have a multiplicative inverse. That nothing multiplied by 0 gives you a 1 modulo anything at all, right? Okay. So this is true. Now, why do we need these extra coefficients? In order to actually, these coefficients give us the multiplicative inverse. The Euclidean algorithm tests that a number is coprime with the modulus, and therefore in multiplicative inverse of it will exist. But what is it? That is actually given by the extended Euclidean algorithm. So what? If I want to, I have my modulus is n, and I have some number mod n, so between 1 and n minus 1, that I know it's a coprime with the modulus. Perhaps because n is prime, so everything is co-prime, or because n is not prime, but my number in Zn is nevertheless co-prime with that modulus n, like 1 and 5 in the example of n equals 6. So now by the Euclidean algorithm, I know, extended Euclidean algorithm, I know that these S and T that satisfy this, they exist. This is not a trivial thing that if n and x are co-prime, then these multiples exist. But it is, that follow from the Euclidean algorithm. A Euclidean algorithm computes them, so obviously they exist. By correctness of the Euclidean algorithm, we can conclude that these things exist. You can find some more direct proof of this as well, but that's a proof as well. So now this coefficient is a multiplicative inverse of x mod n. So mod n, these two numbers are the same. Okay. Why is that? So, okay. Okay, before I say in general, so let's look at an example. I want to compute multiplicative inverse of 54 mod 79. I run to GCD to test that they are co-prime. And the Euclidean algorithm makes a few, recursions, but not too many, right? Because, as I said, Euclidean algorithm, as we argued, is reasonably fast. Is linear in the number of digits, which is 2 here. And it will find these coefficients. So in particular, okay, I'm just telling you that this coefficient will be 13 and minus 19. In other words, 13 times 79 plus minus 19 times 54 is 1. So t is minus 19. And the answer, when I ask you, what is multiplicative inverse of 54 mod 79? Do not tell me minus 19 itself, because that's another number mod 79, okay? Modular reduced mod 79, give me an answer in z of 79, which is between 0 and 78. It's 60. These two numbers are the same. So the 60 is a multiplicative inverse of 54. And why is this? So look in a general form here. A multiplicative inverse of x is some number of b, such that mod n, such that the two multiplied mod n is a unity. Now that holds if and only if x and b and a unity are, at a distance that is some multiple of n, right? That's what the modular reduction means. This number can be represented as the right-hand side, which is 1, plus some multiple of modulus. And I just, now let's move it on this side, right? So m is minus s, and b is t. This equation is the same as this one. I just move s and n to the right-hand side, right? So finding these coefficients basically solves this equation. And once you solve this equation, then x times b is 1 modulo n. And therefore b is the multiplicative inverse of x mod n. Right? Okay. Okay, you know what? I think that's a good place to stop. It's let's do this next time. Okay. If there is some questions about any of these algorithms, and by the way, if something is not quite all right, then say so during slide. I will stop recording. I think that will make you more comfortable. So bye to everyone who watches us offline.